Okay, hello everyone. Welcome back to the AutoML seminar. I hope you all had a great time at the AutoML conference last week in Paris. So today we have Robert here. This is actually a second talk at the AutoML seminar. Robert is a PhD student at the TU Berlin and also works as a full-time scientist at Sakana.ai, and he's also founding member of Sakana AI. And he's going to talk about their latest work on AI scientists, which is very exciting work and hopefully not going to replace us all. With that, Robert, please take it from here.
Thank you, Aaron, for the invitation and for the kind introduction. As already said, I'm Robert. I'm a research scientist and founding member at Sakana. And today I'm going to present to you our work, The AI Scientist Towards Fully Automated Open-Ended Scientific Discovery. And a disclaimer up front, I'm only representing or presenting this work as part of a larger group. So this work was led by Chris Liu, Som Liu, and me, and was supervised by a set of fantastic supervisors, including Jacob Förster, Jeff Clune, and David Ha. So to get started, I kind of want to take a step back and to sort of look at the timelines of how AI or machine learning have sort of progressed over the years. When you look at sort of image generation, we've seen vast improvements sort of starting from GANs and VAEs through things like DALL-E, diffusion models, and now towards models like Flux1, right? And sort of what you can take away from this is that usually these types of generative methods, they start out being fairly rough and generating sort of first results, but not necessarily perfect results. And then over time, they improve quite drastically. And sort of the same phenomenon we have seen throughout different modalities, including text and video, for example, where we've seen things like RNN-based language models and sequence-to-sequence models. And now sort of with GPT-4o or o1, we're at a point where there are many, many different options that are really, really capable. And they're not only sort of closed source frontier models, but they're also open source models, which were developed sort of by the community, and we could iteratively improve over them by sort of all collectively working with them. Again, the same story for video generation. Throughout the last years, we've seen sort of extremely strong progressions or improvements in these types of methods. But for scientific discovery more generally, we've mostly seen sort of AI be used to replace certain parts of the scientific discovery loop. Like, for example, in AlphaFold or AlphaTensor, where AI is used to discover something new, but in the end, like the human still baked in a lot of knowledge and had to essentially come up with the algorithm and then perform the writing and like the hypothesis generation basically manual. So what we wanted to do in this project is sort of take a more holistic approach and see whether or not current frontier language models are capable to essentially conduct research end-to-end, including idea generation, including code execution and modifications, as well as writing up and potentially even like reviewing the papers that were generated in the end. Okay. So that's sort of what we wanted to do. And the takeaway again from this slide is that there are improvements over time and like the collective effort of all of us, essentially, that lead to a democratization, improvements, and validation of the methods that are developed in generative AI. And so far, as I was already alluding to, language models have not been used to essentially automate the entire pipeline, but more as sort of drop-in replacements for a type of evolutionary mutation operator, if you will, right? So in this setting, you use an LLM to construct certain code proposals, for example, and then you would evaluate them on a task downstream, get some type of fitness measure, and feed that back to the LLM context to essentially have a clever or smart proposal mechanism, which does not only operate on sort of numerical values as with Bayesian optimization, for example, but actually can also work in different types of fields like language and so on. And there's been like a vast array of related work in that area, including sort of work by Lehman, where sort of LLMs were used to evolve or construct morphologies of a robot. Eureka, where LLMs were used to come up with reward functions. Evo prompting, where LLMs conduct essentially architecture search, and so on. And basically leading up to this project, me and my collaborator, Chris Liu, we worked together with friends from Cambridge on sort of seeing whether or not you can use LLMs to also discover objective functions for preference optimization, for example. And there we sort of came to the conclusion or idea whether or not it's possible to do even more with frontier models, right? Can we do more than just sort of propose individual code snippets and then evaluate them? Can we essentially try to do more, right? And this sort of feeds into this overall perspective that science is more than just sort of proposing hypotheses or code snippets. It's something that comes in many different stages, including sort of the problem identification, hypothesizing about different solutions for it, brainstorming with other colleagues, and then running experiments, writing a paper, reviewing the efforts, iterating over them, and then in the end, sort of diffusing the knowledge to the community, right? And so therefore, we sort of asked whether or not it's possible to do everything or almost everything of the entire scientific pipeline with a frontier model, basically. Okay. And the approach that we take is the following. So I'm showing you here sort of the general workflow of our agentic pipeline for conducting AI science end-to-end. There are essentially three main stages. The first one is basically you ask an LLM for an idea. And we do so by providing essentially a template experiment file. Like, for example, you could imagine this could be something like a simple training script in PyTorch for endless classification. And then we ask for ideas. We check the novelty of the ideas using Semantic Scholar and sort of relate it to different works that has already been published. We score the ideas for their novelty. And then given that this idea that was generated passes our filtering process, we essentially take it and ask a frontier model to implement it in code. So basically it executes code diffs to the template to implement the idea. And then given this experiment script, we run experiments and collect the results. And basically the frontier model then can use the results that were extracted or created by an experiment to update its own plan and do so iteratively. And then in the end, we have a set of numerical results as well as plots that were generated autonomously. And we use them together with notes, which were created by the LLM to write a manuscript. And again, we use frontier models also to write the manuscript. And then in the end, we sort of wanted to have a way to automatically assess the quality of the work. And basically what we do there is we construct another agentic workflow where the manuscript is essentially, or the text from the manuscript is extracted and then reviewed by this LLM agent. And this review comes in the form of like a standard NeurIPS guideline template, which is then filled by the LLM. And in future work, or how you could imagine this playing out, is that this is done in a closed loop, right? So not only doing this once, but essentially generating papers, reviewing them, adding them to an archive, and then iterating over it. And don't worry if this is a lot, we're going to go through every single step in much more detail now. Okay, and maybe one thing I didn't mention yet, if you have sort of clarifying questions, please feel free to interrupt me during the talk. If you have sort of more philosophical or critical or fundamental questions, then we can maybe discuss them at the end of the talk. Good. So let's get started with the first part of the AI scientist pipeline, the idea generation part. So basically, like I already said, we as the human only provide basically an initial seeding of a potential experiment that you can run. And this is this experiment.py file, right? And we provide that experiment.py file in context as well as like a broad task description. And then we ask, given a set of, or a single basically idea seed essentially, whether or not the LLM can propose new and novel ideas based on sort of these this information provided in context. And here we again use sort of tools from sort of prompt engineering, like for example, reflection or chain of thought or a few short examples, and come up essentially with new ideas. And after these ideas are sort of generated, we use, as I said, Semantic Scholar and the API to essentially validate if there is already closely related work out there. So this is essentially the novelty checking part where we query different papers from Semantic Scholar, and then we use the LLM to compare essentially the abstract with the idea that was generated by the LLM before. And here I'm showing you basically an example idea. So this is in the context of 2D diffusion models. And the template, or basically the JSON format that the LLM outputs, looks as follows. So basically you have a name for the idea, which is adaptive dual-scale denoising. You have a title, adaptive dual-scale denoising for dynamic feature balancing in low-dimensional diffusion models. And then you have an experiment section, which essentially outlines the plan of the experiment, or of the research idea to be conducted, right? So here, the idea goes as follows: modify an MLP denoiser to implement a dual-scale processing approach with two parallel branches, a global and local branch. And there you essentially introduce a timescale specific conditioning weighting factor to essentially increase the parameters, or like the capacity of the model, and to perform essentially generation at different sort of scales. And below here you have four different sort of scores, or variables. One is sort of the interestingness as scored by the LLM, the feasibility, so how feasible it is to implement it, the novelty compared to sort of related work, as well as this whether or not this idea is truly novel, in the sense that we should execute it downstream. Good. And given this idea, we move to the second stage, where essentially we take the idea together with the experiment template and we implement it using code diffs via a tool called Aider. And if you don't know Aider, I think you should. Aider is an open source software agent, if you will, which implements code diffs based on natural language instructions. And we chose Aider because Aider performs extremely well on the SWE benchmark, right? So essentially, as you can see here, these are sort of percentages of GitHub issues that are completed basically by Aider in combination with different frontier models, right? So here, GPT-4o, as well as sort of Claude Opus, together perform extremely well. And we found in our experiments that this is a really, really robust way to implement code diffs given an idea from an LLM. And yeah, so as I already said, we leverage Aider Chat in order to iteratively implement these experiment plans and to essentially get a code level implementation of the idea that I showed you before. And then Aider, or like the agent, autonomously executes the idea like an experiment file basically, and generates numerical results. And here you can see sort of the general prompt that we give Aider. So here you can see it goes as follows. Your goal is to implement the following idea, title, and then the idea is sort of outlined. So this is the experiment plan, for example. And we tell it, okay, there are so many experiment runs. There's a maximum budget that you can have. Please sort of allocate the experiments that have to be run in order to implement the idea, basically. And then Aider sort of first comes up with a plan, and we provide some baseline results. And then here you can see that the experiment is always executed using this Python experiment.py command, which is then executed. The results are generated, and they are fed back essentially into Aider to replan. Good. So far, we've essentially looked at two parts of the pipeline, one being the idea generation, the other one being the idea sort of implementation via Aider. And here you can see for the example that I showed you before for this 2D diffusion task, how Aider would essentially implement this global and local network. So everything you can see in black and in red essentially is what was given by the template, right? And in green, you can see the code is performed by Aider, right? And what you can take away here is that it correctly sort of implements the global, the local network, as well as this weight network to essentially balance these two. And that it essentially kind of increases the number of parameters and adds capacity. And again, on the right-hand side, you can see then how this neural network module is implemented as a forward pass and how this essentially works. And again, sort of just highlighting again the open source contribution in Aider, the code agent is pretty smooth, and here implements a mixture of expert style diffusion architecture if you want. Good. So given these code diffs, we can then generate essentially different experiments and run them to create a set of statistics we could want to write something about. And the writing itself is again done by an LLM. So basically what we do is we construct a priori like a simple sort of LaTeX template for a paper. So this could, for example, be like the upcoming iClear conference submission template. And in order to essentially prompt the LLM correctly, we use a set of sort of manually or blog post inspired criteria for how to write a paper, right? So Jacob Purser, one of the supervisors on this project, had like a pretty, let's say, popular Google Doc in which he sort of outlines how to write ML papers, including sort of abstract, introduction, related work, running ablations, and so on, right? And so basically we use these types of tips or instructions to pre-fill like our template. So basically these are turned into LLM instructions. And then given a notes file, which was generated with the results from essentially running these experiments, we then query the LLM multiple times to fill in the template, right? And again, this is sort of done in a per section way, right? So first we would fill in the abstract, then the introduction, and so on. And we would have like a basically an iterative process where we do this multiple times. And again, here, basically the code agent rewrites directly into the LaTeX template. And then once this is done, we compile the LaTeX basically and get a nice PDF manuscript out. Good. So in order to assign credit sort of to related work, we again use Semantic Scholar, and we basically query for all the relevant papers and then integrate them as BibTeX citations in the manuscript, right? So we essentially provide like a summary of the paper and then ask for specific citations for the individual sections and thereby get the related work. And maybe as like a brief disclaimer, right? We're not claiming that this is perfect. Like we've seen that there can be small biases sort of to very popular papers out there, and we're sort of currently working on improving on these shortcomings. But I'm going to talk about this later. Okay, so now we essentially have all the three different pillars sort of together, right? The idea generation, the code implementation, as well as the write-up part, essentially. And what I'm showing you here now is essentially, yeah, it's low resolution for now, sorry. Basically the example paper that was generated for this dual scale diffusion approach, which we had sort of as the walkthrough example, right? And what you can see sort of from a glance already is, okay, there are figures, including sort of generated samples from the diffusion model. There are plots for like these weight coefficients in the dual scale approach. There are tables sort of highlighting the numerical results, as well as equations, for example, summarizing the approach, and a set of citations. So basically what we did here is we went basically end to end from a experiment template via LLM-driven idea generation, LLM-driven code diffs, LLM-driven experiment execution to LLM-driven paper write-ups. And we get results which look very good and which, yeah, are very nice, right? So if you want to sort of check some of the quality yourself, we're providing all of the code as well as the artifacts generated open source via the GitHub repository and like a attached Google Drive, basically. So I think if any one of you is critical of what we're doing, that's great, right? Again, like sort of communicate, like the community has to sort of democratize and collaboratively improve and criticize over these things. But I would recommend just checking out what kind of papers we generated if you want to get a better picture. Okay, so now sort of the obvious question is, what is the quality of these papers, right? And I think in total we generated like 600 AI generated papers, and like manually going through all of them and sort of assessing their quality is something that would have been very, very time consuming. So what we wanted to do instead, as a first step at getting a better feeling, is to see whether or not we can also not only automate the writing and the sort of scientific research part, but also the reviewing part. So we came up with yet another LLM-driven agent for reviewing. And this agent essentially takes the generated paper that I showed you before, extracts the text from it, and then basically tries to conduct a review as would have been done at NeurIPS, for example, right? So the system prompt is here: you're an AI researcher who's reviewing a paper that was submitted to a prestigious ML venue. Be critical and cautious in your decision. If a paper is bad or you're unsure, give it a bad score and reject it, right? And then the review prompt essentially is a review form. So here we use the NeurIPS reviewer guidelines as sort of the base instructions, and then have a few shot example. Oh, there's a typo in here. A few shot example that sort of gives a paper as well as a review that corresponds to that paper. And then we provide the new paper that was sort of artificially generated and ask for a review. And in order to sort of benchmark this approach, we try to compare this with reviews that were already conducted previously, right? So for example, for iClear, I think 2022, like all paper reviews are publicly available and can be scraped, right? So what we did is we took 500 of these randomly sampled and looked at whether or not, if we provided the paper and to the reviewing agent, the decision that came out was accurate, yes or no. And sort of as a golden baseline, we used sort of data that was extracted from the NeurIPS consistency experiment. So if you remember, like a while ago at NeurIPS, the organizers conducted an experiment where they showed the same paper to different sets of reviewers. And what they wanted to sort of achieve is get an estimate or a feeling for how well human reviewers sort of align in their decisions. And from the experiment, we could extract essentially a set of baseline metrics for how accurate these decisions are, and how essentially the false positive rate and false negative rate looks like for human reviewers, right? And so what we're showing you here is a set of two results, basically. So we differentiate between uncalibrated and calibrated. Let me explain what that means. So the reviewer basically outputs a review score as well as an overall decision, right? So the uncalibrated decision is just sort of the raw decision, accept, reject, while the calibrated one is where we threshold the overall score, basically. And what you can see here is how different language models with different prompting strategies perform, essentially, right? And what you can see here is that GPT-4o with a one-shot example and a threshold at a score of 6 basically performs almost on par with a human reviewer, right? So you can see that the balanced accuracy is 0.65, while the balanced accuracy for a human would be 0.66, while sort of the false positive rate is a bit higher for the calibrated LLM, while the false negative rate is a bit lower, right? And what we can also see is that our agentic pipeline, which uses basically a one-shot example, 5 reflection rounds, and an ensembling of the reviews with a meta-aggregation, performs essentially best when comparing them, the different settings. So it's maybe important at this point to state that we're not aiming to replace human reviewers with the LLM reviewer, but it's more to say that we have an agentic pipeline which can assess quality of generated papers or real papers in a way that is correlated with essentially human reviews. Okay, so maybe now let's take a step back again and look at how one of these reviews looks like. Okay, so basically what I'm showing you here is the LLM review for the dual scale denoising paper that I sort of showed you before, right? And here again, sort of the structure of the review looks very similar to like how a NURBS review would look like. You have a summary of the paper, which goes as follows. The paper introduces an adaptive tool-scale denoising approach for low-dimensional diffusion models, aiming to balance global and local structure, blah, blah, blah. And then you have a list of strengths. It's a novel approach. It's a comprehensive empirical analysis on multiple 2D data sets, yada, yada. And you have a set of weaknesses, right? And here are sort of weaknesses which you probably, or at least I have encountered before. So there are things like that it lacks detailed theoretical justification, and that the computational cost is significantly higher. So it has correctly inferred that essentially a single forward pass through this diffusion model requires more flops. Some sections are not clearly explained. There's a limited diversity in the data sets, and so on, right? So the weaknesses are actually accurate, right? So they make a lot of sense. And then there are different sort of numerical scores for originality, quality, clarity, significance, as well as questions and sort of more broader limitations. And then, as I was sort of alluding to, there's an overall score of a 5 and a decision which would be reject for this paper. Yeah. And what we basically wanted to get out of this is, like I said, an initial sort of estimate for how well did the AI scientist paper look or compare to sort of real human data, human papers, which would be accepted in a conference. A little bit more data on sort of the evaluation of this reviewing agent. Here on the right-hand side in this bar plot, you can see sort of how the individual changes in the agentic pipeline, as well as the foundation model, which we use for reviewing sort of affect the performance. And you can see sort of Sonnet performs the worst. Like in my experience, Sonnet was oftentimes very positively biased and wanted to accept basically all papers. While if you sort of move from Sonnet to GPT-4o Mini to GPT-4o, you can already see like quite the strong increase above sort of the baseline of rejecting all papers. And then if you successively add 5 rounds of reflection, ensembling reviews over 5 agents, as well as sort of providing a one-shot example of a review, you can see sort of the performance which we ultimately sort of achieved with this LLM agent workflow. And here on the bottom, again, you can see sort of from left to right, if we add these components like reflection, ensembling, and one-shot examples, like the accuracy and the false positive rate, false negative rate, sort of they improve throughout. One thing which we also wanted to look at is basically the consistency between the LLM mean review score and the open review mean score, basically, right? So what we wanted to see is whether or not the LLM decision is more consistent with the sort of mean reviewer than the individual reviewers compared to each other. So here on the left-hand side, for example, we're looking at 2 reviewers from Open Review, like human reviewers, right? And how their numerical scores sort of correlated with each other, right? So we always randomly sample 2 of them, and then we plot essentially for a given paper their scores. And you can see here that the correlation between the 2 is around 0.14, right? Well, when we take the LLM review score for a paper and compare it with the mean score of the individual or of all reviewers for a specific paper, we can see that the correlation is actually 0.18, which is higher in this case than 0.14. So it seems like, at least from our initial results here, that LLMs tend to, essentially consistently or more consistently reflect the mean reviewer than individual reviewers, versus each other, basically. Okay, so now we've basically spoken about all 4 parts of the pipeline: the idea generation, the code level implementation, execution, as well as the writing and the review. Let's now look into how well essentially different foundation models on different tasks work. So I was already talking about this 2D diffusion template where we looked at sort of small scale data generation. But we also looked at, for example, a nano GPT style transformer template, as well as grokking, like this phenomenon of sudden generalization in transformers when training, for example, on arithmetic tasks. And we chose these three distinct subfields of ML to essentially explore with the AI scientist and to sort of assess how well it performs in sort of different sort of, let's say, subfields, which, highlight maybe different shortcomings, for example. And for all of them, we ran essentially 200 paper generation experiments. And here we're sort of highlighting 10 selected papers, which we also sort of go deeper into in our sort of meta report on the AI scientist. So you can see here sort of for diffusion papers, to nano GPT papers, and for grokking papers, all of them have a, I guess, a nice title, which is sort of separated by sort of a column, which is kind of interesting. This is like a pattern that was brought to our attention only after publishing. And you can see sort of the LLM reviewer score over here. So it seems like the generated papers right now are not yet at sort of the stage where they would be just accepted at a conference, but they are definitely at a medium quality, maybe like a workshop publication, and for sure, like a really, really talented master's student, I would say. So how does this essentially look like for different models on these different tasks? Here we're showing basically for nano GPT, diffusion, and grokking, the LLM reviewer scores for 4 foundation models across 50 generated papers each, right? So you can see that Sonnet, for example, performs consistently the best, I would say, across these 3 tasks, followed by probably GPT-4o, and then DeepSeek. And Llama 3.1, this is the 405 billion version, tended to perform the worst. And you can see that even though like the closed source frontier models are the best, DeepSeek is actually not far away, I would say, right? And it turned also out that DeepSeek is by far the cheapest option when using, for example, the Open Router hosting. Let me talk through sort of again, the costs as well as the robustness of this approach. So in this table, we're showing basically how the different frontier models sort of robustly were able to generate papers in the end, right? So all of them generated 51 ideas, and then only a subset of these 51 ideas were essentially deemed to be novel, right? So for example, for Sonnet, 49 out of these 51 ideas were novel, while for example, Llama 3.1, only 31 of them were deemed to be novel. And then given these ideas, we then used Aider again with the frontier model as a backend to conduct the experiments. And again, you can see sort of consistently out of the novel ideas, Sonnet had sort of the highest rate of completion. And then after the experiments are run, again, Sonnet had the highest rate of paper completions, basically. Here in the 2 columns, we show you the mean review score across these completed papers. And we can see sort of the, for diffusion here, like, again, Sonnet has the highest average score as well as the highest max score. But then again, as I was already alluding to before, the total costs for these closed source frontier models is a lot higher than for the open source one, and is actually extremely cheap for DeepSeek. So in our paper, we kind of highlight that we're now at a point where we can basically create medium quality papers for extremely cheap cost, right? So on average, including compute, a paper that was generated by the AI scientist cost around $15, right? And I think it's pretty important to highlight that if you compare this with like a starting PhD student at the beginning of their PhD, there are a lot of human capital costs associated with sort of that, as well as probably some cost initially where they just have to get started, right? So I think there is most likely a space where these types of medium ideas can essentially be autonomously generated to allow us humans to work on ideas that we like more or that we find more interesting and so on. But I'm going to talk about this later. Okay, so here again, takeaway, Sonnet seems to perform best, but DeepSeek Coder is also fairly robust and the cheapest. Now, I kind of want to transition into the next part of the talk, where I just want to highlight a couple of anecdotes as well as sort of intriguing findings that we had when sort of running the AI scientist. So it's hard to explain, but it's quite the magical moment when you open one of these generated PDFs and you see a plot you've never seen before, or some idea or some result which you hadn't thought of before, right? It feels really, really special, and especially when this is sort of all done autonomously. And so one thing I wanted to highlight is that we provided sort of this template with sort of base plots, like, for example, learning curves and so on. But most of the time, or oftentimes, it happened that basically throughout running the AI scientist, many new plots were generated, right? Plots that we didn't sort of give initially in the template, and that sort of highlighted different parts tailored to sort of the idea that was implemented, right? So here for the dual scale diffusion paper that I highlighted before, you can see sort of these weights for the different components are uploaded over time, and you can see sort of the modulation dynamics between. Furthermore, for a different paper called dual diff, we basically saw sort of heat maps of the different generated samples with sort of their gating weight color coded. Another thing which I found really sort of powerful and surprising as well is sort of the depth as well as sort of the novelty of the generated ideas. So during my PhD, I at one point worked on sort of this lottery ticket hypothesis phenomenon of sort of training sparse neural networks and sort of achieving sparsity by doing something called iterative magnitude pruning and sort of relating this to loss landscape dynamics and so on. And in the grokking template, the frontier model actually came up with an idea that related lottery tickets with grokking and looked at essentially how the generalization speed or the point of generalization relates to pruning and sparsity in the neural network, right? So this was actually like an idea I was really curious about to see after I saw the idea before, or like the implementation to see. And I think there are many of these ideas where for a frontier model, it's essentially easier potentially to interpolate between different subfields than it would be for a human, right? So in some sense, none of us has read all of the machine learning literature, while for a frontier language model, like it has been pre-trained on a lot of different subfields. And like in the spirit of interdisciplinarity, right, there are many different sort of connections one can draw between them.
Well, a quick question here. So those plots, just to make sure, so those plots are generated by the LLM. So those are not basically actual results of the experiments.
No, so basically the LLM writes the matplotlib code that generates these results. So they are so basically the plots that, or the data in the plots is generated in like a file when running the experiments. And then we have a plotting script that is also edited by the LLM that then visualizes them.
Oh, okay. So those are actual results that you're plotting there essentially.
Absolutely. Like everything or everything that we highlight, we triple checked for sort of hallucinations and so on, and found them to be accurate, basically. Yeah. Good. So these are just sort of two of my sort of favorite things about this project, sort of being surprised by opening papers and seeing new plots, as well as sort of seeing new ideas which we hadn't thought of before. And you can check out all of these papers again online and sort of make yourself a picture, and feel free to open an issue or to criticize as much as you want. Good. One other anecdote, which sort of raises the point of the safety and the ethical concerns of this project, is that we saw oftentimes, or not oftentimes, but sometimes, that basically the code level changes sort of try to essentially hack what we were doing, right? So one thing that we saw, for example, was that it happened once that basically within an experiment file, the experiment file was called again, right? So usually this should only happen sort of on the outer loop level, but instead sort of Adria had edited, or the frontier model had edited the experiment file generation already into the experiment. So you had like a recursively building up stack of programs to be executed, right? Furthermore, we saw something where the LLM tried to modify the time limit for a specific experiment. So what we did in order to to sort of constrain the experiments is we set for an individual run, you have X amount of time to complete, right? And if this didn't succeed, right, it happened once that basically Ada tried to increase that time limit, right? So these are sort of two important sort of lessons where we going forward have to make sure that we do proper sandboxing and proper constraining of the resources, as well as runtime, as well as sort of what packages are imported by the AI scientist. And we had sort of more of these types of anecdotes where sometimes we had checkpointing in the experiment, and instead of checkpointing at a specific lock interval, which was reasonable, like basically Ada and the LLM try to save a checkpoint every single SGD step, sort of leading to our disk running out of memory, for example, and these types of things. Okay. And now I'm sort of getting sort of towards the final part of the presentation, namely sort of some of the obvious sort of limitations on the technical side, as well as what we want to do in future work. So basically, there are a bunch of low-hanging fruits, for example, for improving the pipeline of the AI scientist, including sort of tuning the prompts which we use, using larger templates with more sort of compute required, as well as, for example, keeping an idea archive where the different ideas are basically used to see the context of the LLM, for example, or to essentially integrate multiple ideas together. Another shortcoming, which we want to work on, is sort of iteratively using the reviewer feedback that we get, not only at the end to assess the quality of the paper, but essentially to improve the paper in an end-to-end fashion, right? So this is basically closing the loop, where instead of just getting a review and saying, okay, this is a bad paper, we can essentially have the limitations and weaknesses feedback into the AI scientist to address them properly. Another thing we're excited about is sort of the automatic design of such AI scientist pipelines, where you could think of either sort of running the AI scientist in a meta self-referential way on itself. So basically asking ourselves how to conduct science of science in an empirical way and not only in a philosophical way, or using types of evolutionary optimization, like a recent paper by Jeff Kloon's group called Automatic Design of Agentic Systems, to essentially end-to-end improve how we conduct research with the AI scientist when trying to, for example, optimize something like the acceptance ratio or something like that. And then something else which we're currently sort of lacking is something I already alluded to, like a certain degree of depth in the experiments. So basically what we focused on so far is looking at sort of the width, so running many experiments on many ideas with different foundation models. But there are definitely many things to be done to essentially make an individual experiment or idea much deeper in terms of reasoning through the results that that came in before. Good. So now sort of let me come to probably one of the most important slides of this talk, namely sort of with regards to the ethical considerations. And again, like a disclaimer, these are definitely not all ethical considerations one can have with regards to the AI scientist, but these are a couple ones that we wanted to highlight. So one of them is what I already spoke about before, namely safe code execution and containerization. So you don't want the AI scientist to install packages or import packages that you don't want, essentially. And this has to be ensured either by using sort of a Docker container or restricting like the resources that are being associated with the AI scientist. Another sort of important part of this is that we are very passionate about people making sure that they are completely transparent about whether or not a piece of scientific material has been generated by a foundation model or by a human, right? So basically, we made sure that in all the papers which we release, we add a watermark which basically states, okay, this paper was generated by the AI scientist. And I think in general, this is something that conferences should adopt or are adopting, where even though you're maybe only using LLMs to write, it's important to make sure that no one is sort of how do you say, like, perceived or deceived in the sense that they think it's something that was human generated. And then something else I think is sort of at the crux philosophically of this project is sort of the definition of a scientific contribution. So we chose, for example, the paper format as a medium to communicate the results that were generated by the AI scientist. But if you think about it more deeply, oftentimes for me at least, the biggest contributions to science are not necessarily the papers or like how many citations a paper gets, but much more about sort of how well, easy, and effectively does it diffuse into the community, right? So if you, for example, think about residual nets, right? They were such a big success because residual connections are like a two-line code change, right? So it's basically something where the degree of adoption is much more indicative of the success of the paper than sort of just citations of papers, which might not necessarily have diffused as well. Okay, so one thing one could imagine is not optimizing for review scores, but optimizing for sort of GitHub stars in the long run, or how easy it diffuses, right? And one could also think of maybe we don't want to stick with the old format of the paper, but sort of move towards new formats like, I don't know, blog posts and so on, which might even be easier to digest and to communicate science. Okay, and then finally, we are interested in sort of seeing whether or not we can establish more robustly sort of the performance of the LLM reviewer on sort of new papers which have not yet been reviewed before and might not be entirely part of the training corpus. And then we're looking into what can be done from the community side to make sure that once we get the first AI written conference paper, the signal to noise ratio between sort of AI generated papers and human generated papers remains sort of good. Right? Okay, and this is sort of one of the last things I want to talk about, namely sort of our perception of how science works. So I feel like oftentimes people have this idea that Albert Einstein woke up and sort of the idea of relativity theory just came to his mind. He wrote it down, and that was it, right? So he had like this flash of thought. But in reality, most of creative efforts are not like 0 to 1 processes, but they are much more, I would say, like continual and lie sort of on a spectrum, basically, right? So if you think about the invention of Cubism by Picasso, it's not like Picasso just sort of thought of Cubism and then gifted it to the world, but instead it's much more like there were contemporary artists like Joan Gris, Joan Miró, and Salvador Dalí, which essentially all inspired Picasso and led him to sort of position himself within potentially this convex hull of different concepts that were already out there. So therefore, Picasso already sort of coined this phrase, good artists copy, great artists steal, right? And stealing not in the sense like they take away or they plagiarize, but much more in the sense like they take different concepts from different sort of contemporary work, for example, and compose them into something novel. And to me, sort of the big question is whether or not foundation models right now are good thieves in the sense that they, like I already said, compose, transform, remix, and tune sort of results that are already out there, right? And I think even if LLMs might not necessarily be suitable to do extreme extrapolation and then completely new fields, if they're only capable of interpolating between like the knowledge that was already established by sort of the human society, I think it's going to have a huge impact on how we think about innovation and how much automated science there will be in the future. Okay, with that being said, I think one of the big visions of like the people I worked with on this project is whether or not we can at some point in the near future even imagine having an AI conference. So basically a conference where all the papers that are submitted or generated by AI scientists, they are reviewed and then also communicated and meta archived or reviewed by a type of artificial area chair, for example, right? And in principle, this is already possible right now, given like the Open Review API and how easy it is to essentially, conduct conferences in a programmatic fashion nowadays. With that being said, I think one last thing that's important, and which I already tried to highlight before, I don't think we're going to replace the human entirely in the scientific loop, but I think much more that it's going to help humans sort of focus on what they are interested in and what they are really good at in science. So, for example, I like to quote the coach of Boris Becker, which was like a famous German tennis player, who basically had the philosophy that with Boris Becker, he wouldn't train on his weaknesses, but instead sort of only train on his strengths, right? So I think there is something to us human researchers thinking deeply about like what is the most fun for us and what are we best at, and then to essentially fill in the other parts with frontier models, for example, right? And with the AI scientist pipeline, you can modularize it, right? You can only take the idea generation part, you can only take the experiment coding part, you can only take the writing part, and essentially help it in your workflow. And in the long run, I think the human is ultimately the one who's going to steer the research directions and to basically has to decide which direction is good and which is not. And this is something that is going to ultimately have to happen in an open-ended fashion and potentially in a type of pick breeder setup where the human decides between whether or not multiple options are better or worse and to rank them. And now I'm going to conclude. Again, like all the results are, and the code is openly available in our GitHub repository, github.com/AI scientist. Feel free to play around with it. Feel free to use your own template. And with that, thank you very much. And I'm looking forward to your questions.